Hey guys, welcome to day 4 of 28. So first of all, I do want to put these things on YouTube, but I don't feel comfortable doing that unless I hear from everyone that they are comfortable with it. So I certainly wouldn't want to make anyone, feel uncomfortable about having lectures that they participate in appear on a public platform. And so I've posted the link to the survey in the chat. Now, I'm asking for your name in the survey just so simply I can go through the course roster and just make sure that everyone who's in the course has agreed. If the answer is no, though, you do not have to put in your real name because I understand that, I'm evaluating you, et cetera, et cetera. So if you don't feel comfortable, you can just say, you don't have to say your name, you can just say no. Hopefully everyone agrees. Yeah, so the link is, oh, did it not work? It may not have worked. Hold on. Let me share it properly. Share the link. Copy. Okay. You don't have to do it again. You just have to do it once. And I have about 20 responses, but there's 34 of you. And so, oh, it's going well. We're up to 26. So that's good. Again, I think that one of the good things that can come from this whole oh, I see. People that log in after, right? So I'll just keep pasting the link. Good point. Yeah, so one of the good things that can happen from this whole remote learning thing is that the process of integrating technology into higher learning can be accelerated. And so I really want, this is I think the second course that I'm recording every lecture. And then after the course, we can post those lectures to something like YouTube to facilitate. There's lots of people out there learning circuits, and although it's definitely not the sexiest subject, I've definitely benefited from. I watch YouTube for learning every day. And so if I can be a contributor to that endeavor of making information free and easily accessible to everyone, I really want to try and do that. So that's the impetus for asking your permission for that. Because like I said, I don't want to make anyone feel uncomfortable with this move. I also don't want to get in trouble. Who knows what the Graduate School of Engineering policies are for these sorts of things. But I do want to benefit the people all over the world who want to hear an awesome lecture on voltage division from time to time. Okay, let me do what I said I was going to. Oh, first of all, before I get into the review of last class, review of the recording, I do have all the lab components in my office, and I'm meeting with the TAs after this class to start coordinating the distribution of that to you. Let me actually first.
You see the screen?
Yeah, question, yeah.
She's looking forward to God.
Oh, someone's not muted. Let me, I just want to get a sense of how many people are local in New York and how many people are outside of New York. And the reason I say that is because we will ship, the parts to anyone who's not nearby. But for those of you that are in the greater New York area, it will just make, it will make this getting everyone's circuit kit delivered will be a lot easier. We could have you come in, you don't have to come into the building. You can have the TAs or one of my admin people meet you at the door to Steinman or something and give you the kit. That way, the TAs don't have to mail out 34 kits through DHL. I went through the process of actually figuring out, how many resistors, how many capacitors everyone can get. Let me just write this poll. Are you located in close proximity to Steinman Hall so that you could potentially come by to pick up circuit kit? Okay. Let me save this. Let me see if I can now. Okay. So let me know. I'm trying to get a sense of, I mean, it's up to you. If you just don't feel like leaving your house and you live in Upper West Side, you can say no. You don't have to. You don't have to do it. You can wait for shipping, but we'll know from your address how lazy you're being. But yeah, no, we will ship to anyone that doesn't want to, that isn't able to or just refuses to come to campus. I'm just trying to get a sense of how much work this is going to be. But we do have everything ready to assemble and to ship to you. And they're very nice kits. It's very nice equipment this year. You have an oscilloscope, D to A to D. So, okay. It's about half, which is good. So the TAs will have to make 14 trips to the courier. Okay. Let's see. 2 more people have yet to vote. I'll give you guys a few more seconds. So there is a poll active if you can access it. Okay. And in the meantime, what I will do is I will navigate to lecture 2. And okay. All right, I'm gonna end this, close it. Okay, so first of all, is there any questions about last lecture, the YouTube lecture, that you guys want to raise today?
Hello.
Yeah, I hear you.
Yeah, I do have a question about slide 39.
Yeah.
Yeah, so the reason on why the resistors are connected like that, it's just trying to make it seem that the circuit needs to be small or something, or it's just connected like that. Because yes.
Um, no, let's see. Yeah, so I think a lot of it, a lot of the answer to the question is just, I mean, there's two potential answers. One is what you'll see when you do the labs is that the way that a circuit actually looks on your breadboard looks nothing like the diagram. Like the circuit diagram is always cleaner than what your breadboard looks like. Your breadboard will just look like there's wires all over the place, and it's not going to be, it's not going to resemble the nice rectangular drawing here. So that's one thing. The other thing, and so sometimes you'll want to, sometimes you'll look at your breadboard, you look at your wiring configuration, and you'll have like, you know, you may have a diagonal oriented resistor, and so you want to draw like that. So that's one part. The other part is that from from an educational kind of perspective, we want you to be able to understand, to be able to redraw circuits. We want you to be able to understand that any element in the circuit can be redrawn as long as you preserve all the connections. And so it's more of an exercise in being able to redraw a circuit. So for example, for the 6 ohm resistor, one end is connected to node C and the other is connected to node B. So when you redraw it like here, you got to make sure that this end is equivalent to node C. And it is because it's in between the 10, 3, 6, and 1, right? So this node here is node C. So we just want you to get into the habit of being able to expand the node, as was done here, or to collapse it. And so there wasn't, again, this is a very fundamental course on circuits. So we're it's not like that this diagonal shape corresponds to anything physical necessarily. And again, um, you know, if two people have the same physical circuit in front of them, and then they draw a circuit diagram, those circuit diagrams may come out looking different. But if you examine all the connections, you'll see that they are actually equivalent, electrically speaking. So it's just an exercise for you to be able to um, redraw circuits without changing any of the properties at the terminals. Okay, is there any other questions, particularly on the last three? The last three questions are probably the most the most important.
Professor, can you switch for the next one?
44 or 45?
Uh, I'm trying to remember my question. I think it's this one.
Okay.
I was confused about how we derived uh, okay. Is V1 for the 6 ohm resistor the same as the 12 ohm resistor?
Sorry. I'm asking in chat. Is V1 the same as what? Sorry, I'm sorry. Can you repeat your question?
Yeah, is V1 the voltage for the 12 ohm resistor? Is it the
Yes.
same for the 6 ohm resistor?
Yes. The 12 ohm resistor and the 6 ohm resistor are in parallel because they have the same they're connected to the same node at the top and the bottom, right? So the nodes here, let's let's see, if I were to draw the nodes, you know, this is one node, this is another, and this is another. So there are basically, there's only 3 nodes in this circuit, 1, 2, and 3, right? And so the 6 ohm and the 12 ohm are connected to this node and this node, so that they're in parallel, meaning that they have to have the same voltage.
And when we were calculating the current, they don't have the same current though, right?
They do not have the same current. So V1 is 5 volts. We solved that. And so the current through the 6 ohm will be 5 over 6. And the current through the 12 ohm will be 5 over 12
Okay.
because of Ohm's law.
Okay. Thank you.
You're very welcome. Okay.
Professor, why is the arrow of the current going opposite the actual direction of the negative charge current? That's just so confusing. I think it was Benjamin Franklin who first drew that. I looked up, and they just stick with that. Is that true? By convention.
So yeah, well, it has to do with, so first of all, it depends. So part of the problem is that it depends on like the substrate. So so it was very early on in the, when electricity was being discovered and studied, it was initially thought that, or I don't even know if it was thought, but it was just established that we're going to model positive charge moving, the movement of positive charge doing the actual moving, doing the actual traveling. And so that does happen in some like in biological tissue. You do have positive ions doing a lot of the moving. Like if you study nerve cells, like sodium ions and calcium ions do a lot of the moving. And so in the nervous system, that is actually true. But in conductors, in wires, in inorganic matter, it was discovered later on that it's actually electrons that do the moving. But it gets complicated because you have things like holes, which is the absence of electrons. And so that's your positive charge. So basically it's just a convention that we stick to, but it really is, it's specific, it's situation, it's substrate specific. There are some situations where in this course, when you're dealing with circuits, yes, you're absolutely right. It's opposite to the convention in that it's the electrons that actually do the moving, and you can think of the electrons as moving opposite to the direction of the arrow, which models positive charge. However, there are situations in biological tissue where, in fact, the positive charge does the moving. And so, we have a convention, we're stuck with it. And for the sake of your learning, you can just assume that positive charged particles are doing the movement in the circuit, even though that's not physically true. But it doesn't change. It doesn't change the voltages or the currents. It doesn't change their values. If that makes sense. Okay. Those are all good questions. Anything else? I really don't want to move on unless you guys feel like you grasp the content of lecture 2. One benefit of coming back to pick up the circuits kit is that you can pay a visit to Cafe One. That's called reverse advertising. They didn't pay me to say that. Okay. The last question. You mean the last question on the slide? Like this? Sure. Yes, I can go through it. Let me see if I can use the, okay. All right. So we have this circuit and we are asked to find V naught. Well, let's just find V naught, I naught, I1, and I2. So whenever you see us, we see, for example, that the 6 kilo ohm and the 12 kilo ohm are in series, right? So this will be interesting. I will try it. This is probably going to be an epic fail, but I'm going to try. Right. So I can try to do what I undo. All right. Undo doesn't work. Okay, I'm going to give up already. Basically, this part, and this part can be modeled by yeah, there you go. All I had to do was advance the slide. So the 6 kilo ohm and the 12 kilo ohm are in series, so they can be combined into one 18 kilo ohm resistor. And that's gonna, and I2 is gonna go through that path. So we know that this 30 milliamp is gonna be split up into two parts, I1 and I2, right? And so we can actually combine these two resistors because they're in parallel. So 9 times 18 divided by 9 plus 18 equals to 6, right? So at this point, we've reduced our circuit into a single current source and a single resistor.
Wait, I'm sorry, Professor. I didn't catch that. How did you get it to 18 instead of 12?
Yeah, so this 6 here, oops, this 6 that I'm highlighting is in series with the 12. Right, so any current that goes through the 6 has to go through the 12. Right, so I2 here, like any current that goes and that at this juncture keeps going to the right is going to pass through the 6 and the 12, and therefore the 6 and the 12 are forced to carry the same current, which means they are in series. And resistors in series can be combined. Resistors in series can be combined by adding their values. This is what happens with Zoom. Okay. Okay, so we're at this point. So what has that gotten us? Well, it has gotten us V naught. And the reason is, notice that the voltage drop from here to here is equivalent to the voltage drop from here to here, right? And so 30 milliamps times 6L, so I'm not even, sorry, that's another way of doing it, but I just realized what I have on my slide is a little bit different. So we're going to apply current division to this circuit here, right? And so the 30 milliamps gets split up into two parts, part 1 and part 2. So if you remember the laws of current division, the resistor, the branch with less resistance gets more current, right? So this resistor here is 1/3 of the total resistance, 9/27. And so the amount of current that flows through here is equal to 30 milliamps times 18 over 18 plus 9. So maybe I'll try to text this out. So the reason I got this is I1 is equal to 30 milliamps times, and then the numerator is 18K, and the denominator is 9K plus 18K, right? Because current follows the path of least resistance. And so the path here, I1, has 1/3 of the resistance, so we'll have 2/3 of the current. And similarly, I2 is going to equal 30 milliamps times 9K over 9K plus 18K. So again, is equal to 10 milliamps. And this wish they would let you edit these. So basically, I1 is equal to 20 milliamps. Okay. And I can, so that's the 18 over 27 corresponds to 18K over 9K plus 18K. So it's just a rate. This is just a ratio, so you don't have to worry about the units. And then this, the 0.03 is just 30 milliamps expressed as an ampere. Okay. Okay, so I will clear this.
Wait, so Professor, we're basically multiplying like the percentage that would go into each resistor.
That's right. We are
Okay.
multiplying a percentage, exactly, a proportion. And did a question, current division only applies to parallel resistors? Yes, exactly. Current division only applies to parallel resistors, and voltage resistance only applies to series resistors. One person would like to see City College campus again. That's very nice. Thank you. It was nice to see. I'm on campus today. My office needs a lot of cleanup. Okay. That's neither here nor there. Ohm's law. We have I1. We know that I1 is equal to 20 milliamps. And now we want to get V naught. So we know that V naught is equal to I1 times 9,000. Right? That's the literal application of Ohm's law. And so we multiply the 20 milliamps, which is 0.02 amps, times 9,000, we get 180 volts. So now we know the value of I naught. And we're also asked to find the power supplied by the current source. So remember that power is voltage times current. And we know the current of the current source, it's given to us. And this current source is parallel to the 9 kilo ohm resistor. And the voltage across the 9 kilo ohm resistor, we just solved for, it's 180 volts. So we multiply 180 volts by 30 milliamps, and we get 5.4 watts. So that's the power. That's the power supplied by the current source. Just check. I don't think there's any more questions, but I will continue. Okay, so now let's do the power absorbed by each resistor. Okay, so we know that I2 is going to be the remainder between 30 and 20, right? The 30 milliamps comes here to this node, and 20 of it goes here, which means the other 10 has to go through the 6 kilo ohm and the 12 kilo ohm resistor. So 10 milliamps is equal to I2. So now we know the current that passes through each resistor. And so now we can compute the power. Let's first get the power to 9 kilo ohm resistor. Power is equal to V. Let me maybe just annotate this just to make it So the power of the 9K is V naught squared over R. Right, so that's that. So that's how you get the power. I lost my cursor again. Okay, let's see if I can get it back. No. Let me see if I go PowerPoint there. No. Let's see. No, I don't want that. Oh, there we go. Okay. So we know that the power of the 9 kilo ohm resistor is equal to 180 squared divided by 9,000 because power is voltage squared divided by R or current squared times R. And so for the 6 kilo ohm resistor, since we don't know the voltage across it immediately, we can just use current squared times R. So the current.
Professor, you stopped screen sharing.
Oh, that will happen. And I appreciate the quick, correction. Okay. Okay, so to get the power of the 6 kilo ohm resistor, we can use the current squared times R formula. Right, so the current is equal to 10 milliamps, which is equal to 0.01 amps. Square it, multiply by 6,000, you get 0.6 watts. Same thing for the 12 kilo ohm resistor. It has the same current. So I'll go back to the 18 and 27 in a second. So let me just finish this. So the 12 kilo ohm resistor here has I2 flowing through it. I2 is 10 milliamps, which is 0.01 amps. Square it, multiply by the resistance, you get 1.2 watts. Okay, so let's look at this picture. So you have a current of 30 milliamps that's getting split up into two parts. One path into two paths. Well, path A has a resistance of 9 kilo ohms. Path B has a resistance of 18 kilo ohms. And we got the 18 by adding 6 to 12. And so the current division formula, let me just see if I can end show, and I'll show you the picture for, remind you of current division. Yeah, so the current, I'm trying to find the best picture for it. I guess it's here. And so if you consider the, this picture, you have a current I that's entering kind of a split between two nodes. One of the nodes is going to carry I1 and the other is going to carry I2. So we know that I1 plus I2 has the total I. And what we're interested in, what proportion of I goes to I1 and what proportion goes to I2, right? And if you work out the math, you just, math, it's just KCL and Ohm's law combined. You get that the current I1 is equal to R2 divided by the sum of R1 and R2 multiplied by I. Okay, so this is the total current. And then R2 over R1 plus R2 is a fraction. It's a fraction that's greater than 0 and less than 1. So the key thing to note here is that the fraction of current that goes through I1 is proportional to R2. And the fraction of current that goes through I2 is proportional to R1. Because again, current follows the path of least resistance. And so the 18 in our picture, where we have one path that has 9 and the other has 18, the 27 is the sum. So that's the denominator. And the 18 is the resistance value in the outermost branch. And so if you multiply 30 milliamps by 18 over 27, you get the current that flows down the 9 kilo ohm resistor. Okay, thank you. Is there any other questions, comments about lecture 2? Okay. Sweet. I will kill this and go to lecture. So lecture 3, we move on to techniques that are used quite a bit to analyze circuits. So the techniques that we cover in this lecture are, there's 2. One is called nodal analysis, and the other is called mesh analysis. Now, there's a little bit of a preamble about how to solve systems of equations. So I've noticed over the years that the linear algebra that the students come into the course with is not a lot. And so it is assumed in this course that you know some way of solving a system of linear equations. So 3 equations, 3 unknowns, 4 equations, 4 unknowns. I don't care, this is not a course, this is not a linear algebra course, so I don't care as to what approach you take to solve them. So on the homework, if you want to use, you want to do it by hand, that's always the best way for learning. But if you want to use a whatever programmable calculator, that's fine. If you want to use MATLAB, that's fine. I will show you in a second how to solve system of equations in MATLAB because it's I think super useful. Why do I bring this up? Because these techniques, nodal analysis, which is based on the application of Kirchhoff's current law, and mesh analysis, which is based on the application of Kirchhoff's voltage law, they all lead you to a system of simultaneous equations. So a system of equations where you have 2 equations, 2 unknowns, or 3 equations, 3 unknowns. And so the textbook uses this Kramer's rule. You do not need to, if you're not a fan of Kramer's rule, that is all right with me. But I'll just briefly go over it. It's kind of like, it's like a mnemonic. I don't know, it's like a trick. You don't really learn much from it, but it does work. And it is easy. Okay, so Kramer's rule. So imagine you have a system of equations. You have 3 equations and 3 unknowns. So what does this matrix equation mean? It means a11 times x1 plus a12 times x2 plus a13 times x3 equals to b1. So maybe here, what I'll do is I'll kill the slideshow for a second, and I want you to understand what so a11 times x1 plus a12. I apologize to those that this is like too easy and that this is insulting your intelligence. I'm sorry, but I will first I'll move this. Okay, so that first row and first element means, I think I'm trying to move this. right? So that's one equation. When I say 3 equations, 3 unknowns. Okay. So that the first equation in our system of equations here is a11 times x1 plus a12 times x2 plus a13 times x3 is equal to b1. And the second equation will be a21 times x1 plus a22 times x2 plus a23 times x3 is equal to b2. And the third equation is this row times this column equals b3. That's what this is, just a matrix notation where you represent just, you put the coefficients here, and you put your variables here. So the coefficients A and B are given to you in the question. And you're looking to find the value of x1, x2, and x3. So how do you, first of all, solve for x1, x2, and x3? Well, now I will dive, that's what Kramer's rule does, right? So you have this system of equations. Yeah, you don't have to like it. So again, you don't have to use Kramer's rule in this course. I am perfectly okay if you use substitution of variables or whatever method you like. But Kramer's rule just says that the value of x1, which is the first unknown variable, is equal to a ratio of determinants. So determinant 1, this triangle here, I think it's also known as del. I may be wrong about that. So I'm just going to call it del, even though it may not be proper Latin, but del 1 over del is equal to x1. x2 is equal to del 2 over del, and x3 is equal to del 3 over del. So these dels, and YouTube's going to roast me if I use the wrong Latin variable here, is just a symbol for a determinant, right? And so what is the determinant of a 3x3 matrix? I know you're loving this right now. So for a 2x2 matrix, it's easy. If our matrix was just these 4 elements, the determinant will be a11 times a22 minus a21 times a12. Now for a 3x3 matrix, what you basically do is you cross off the first column and the first row, and you compute the determinant of this, right? So what's in the parentheses here is the determinant of that 2x2 matrix. And then you multiply it by the intersection of the 2 crossed out columns and rows. Okay, and then you move on to the second, you cross out oops, hold on, check that. You cross out, let's see. Oh, I think that was right. You cross out the first row and the second column. Let me just make sure I'm getting this right. Yeah, so you do the determinant of sort of like this, right? Right, so a21 times a33 minus a31 times a23, and then multiplied by the intersection of the crossed out columns and rows. With them, every time you add a term, you alternate the plus and the minus sign. So this, I'm just showing you here how to compute the determinant. You don't need to know, if you don't want to use Kramer's rule, you don't need to use determinants. I will show you my preferred way for solving system of equations in just a second. And then the last term here is the subdeterminant a21 times a32 minus a31 times a22, right? So this whole term here, everything here, oops. Just do freehand. So everything that I've underlined here is a determinant of the original matrix here. And so that's your del. And then del 1, okay, come on. Del 1 is obtained by using the same formula, but now and this is where the magic comes in, you're magically swapping in the coefficient vector into the first column and getting the determinant. For del 2, you magically swap in the coefficient vector for the second column and compute the determinant. And for del 3, you magically swap in the coefficient vector for the third column and compute the determinant. And then once you have these 4 determinants, you have the solution of x1, x2, and x3. When I look at things like this, I wonder, how did the lucky man stumble upon this formula? I have no idea. It seems so, it does not seem intuitive, but it does work. It is correct. And if you like determinants, yeah, you go from, yeah, I mean, basically a determinant of a 3x3 matrix is decomposed into a summation of 2x2 determinants. So yeah, you're like, you can decompose the determinant of a 3x3 matrix, but I would encourage you guys to use substitution, or I think you're all eligible for MATLAB license through the school. You can sign up on MathWorks with your CCNY EDU account. And then let's say you have let's say that, let me just first write down what the equations are going to be. Let's say 2x plus 3y is equal to 10. Let's see, let's make x, let's say minus x. I'm just making up some randoms here. I hope this has a solution. So how do you solve this? Well, you solve this by, let me just first verify that it has a solution before I, there you go. 2, 2. So the point of intersection is 2, 2. So, okay. So first of all, right, so this, in this line of code, I don't have to, I wish I had time to teach you guys MATLAB, but I don't. But this line defines a matrix called A. And if you can print out what you define. So my matrix A has 2 columns, 2 rows and 2 columns. And these are the values, 2, -1, 3, 4. And then my coefficient vector, my coefficient vector B is a column vector that has 2 rows and 1 column. Its values are 10 and 6. So here I define my coefficient matrix A, and I define my coefficient vector B. And now I have them in memory. And so if I want to solve this system of equation, the system of equation AX to B, then this is the key line here. X is equal to A, what is that, / or backslash? I always get them confused. Right, so and there's my solution. So in other words, in this original equation, X is equal to 2 and Y is equal to 2. And you can verify that, right? So if you go 2 times 2 plus 3 times 2 equals 210. Check, check. And then let's verify the second equation. -2 plus 4 times 2 is equal to 6. Check, check. We got the answer, right? Okay. So that's how you solve a system of equations. You just define a matrix for your coefficients, and you define a vector for the right side coefficients, B, And then this is the line here that you can use. So I mean, I like that approach because I don't have to worry about if I made a mistake in my algebra or anything like that. And also, this is the way that people's, in modern day problems, your systems of equations have thousands, even millions of variables. So obviously you're not going to be using substitution unless you're a masochist.
Just to add to that, I think it's the A times the inverse of B. If you take the math class 302, they will cover this in class.
Yes.
It's A times the inverse of B, I think.
This will give you the same answer.
Yeah.
Yeah.
Oh.
And so, but the MATLAB doesn't like this. They say inverse A times B can be slower and less accurate than A/B. So it tells you, but yeah, you can always do the inverse. So the way that, let's see if I, let me annotate this. So if you have an equation like oops. So if you have A, this is what my handwriting looked like when I was in grade 8, probably. A times X equals B, where A is a matrix and B is a vector. You can solve this if you multiply each side of the equation by the inverse of A. And again, I really wish that, first of all, can you guys just shut up? Have you guys taken a class on linear algebra?
I'm taking one right now.
Taking one right now. So linear algebra is super important when it comes to like the two subjects that are really important, I think, and this is just my opinion, I'm not the views and opinions expressed by the instructor are not the views of the GSOE, CCNY, CUNY, anyone else that is involved in paying me. It's just my opinion. Linear algebra and programming are the two most important skills. That's where the world is headed. Data. Data is arranged into matrices, and the analysis of that data is performed by linear algebra. So I would pay attention in linear algebra class, even though I know that it's very dry and it's the way they teach it sucks, and it needs to be made more fun. But nevertheless, things like make sure you understand basics like matrix multiplication, inverses, eigenvalues, determinants. Make sure you understand those operations. They will take you a long way. So Sam, did I interpret what you were suggesting correctly?
Yeah. Like it just I want to explain a little bit more because like they will cover that in the 302 class like this semester. So
yeah. So this is so these are the two ways of way number one and way number two. You basically truthfully you are taking the inverse of A and multiplying it by B, but this is a shorthand because in this version, and this is pretty advanced, in this version of the A/B, you do not actually have to explicitly compute the inverse of A. You can solve for X without doing it. And MathWorks, they're pretty neurotic and they want your code to run fast. And so they advise you away from using inf unless you absolutely need it. Yeah, you can use Excel. Programming is the other coding. Learn to code. I'm teaching my 8-year-old how to code. because I'm pretty sure that the world that she's going to be entering is going to be nothing but robots, screens, and so you better know how to program those robots and screens, because I think that's what our world is going to look like soon. Okay. Yeah, definitely. If you can take a programming course, that's amazing. But you can also learn a lot on YouTube, or how, whatever other resources are out there. Okay, so that was kind of a long aside. I'm going to jump back now into nodal analysis. And what is nodal analysis? So it's just a way of analyzing circuits kind of systematically. And what it really is you apply KCL to every node. And so in nodal analysis, you are solving for the voltage at every node. And to do that, you're going to write a KCL equation for every node. So for now, we're just going to assume that our circuits do not contain any batteries in them, no voltage sources. And then when we get to circuits that have voltage sources, we'll tell you how to handle that. Because there's two steps basically to nodal analysis. It's very straightforward. So the steps are, so first of all, you're given a circuit with n nodes without voltage sources. Step number one is you select a reference node. And usually the reference node will be down at the bottom. And that's often called the ground. And then you assign voltages V1 to ... through n-1 to the remaining nodes. And so now every node's voltage is given with respect to the reference. Okay, so if you have 5 nodes, you're going to have 4 voltages. And then the 5th node is your reference. So we typically say that the reference node has a voltage of 0. All right. And then the second step is to apply KCL to each of the n-1 non-reference nodes. And then you use Ohm's law to express the branch currents in terms of node voltages. So when you see these steps written out, it's not always clear what you're doing, but when you see an example, I think it'll make much more sense. There's actually 3 steps. The third step is to solve the system of equations defining node voltages. Okay. So the first step is to define your reference or your ground. So I don't know why, but we have 3 different pictures for the same thing in circuits. We always, you can, if you're partial to one of these 3, by all means, feel free to use them. I don't know, it's not important. And I don't know how he got the 3 different symbols for the same thing, but we have them and they all mean ground and they all mean 0 volts, because the voltage of a node with respect to itself is always 0. All right. So now we have our first circuit. We have a circuit that has 3 nodes, but node 0 here, we're going to call the reference. Okay, so this bottom node here is the reference node, and its voltage is defined to be 0. And this is node 1, and this is node 2. So first of all, I'm just going to stop and make sure that everybody agrees that this circuit only has 3 nodes. And if you're not clear about that, please let me know. All right.
Professor, can you count them again?
Yes. So that there's one, let me use the, so this is node 1. All of this here is node 1. Then all of this, or node 0, I guess. This is node 1. And then all of this is node 2. Remember I said if you can trace your finger between any 2 points in a circuit, right, then it's the same node. So this is node 0 here. Everything that I'm highlighting is node 0. Everything that I'm highlighting now is node 1. And everything that I'm highlighting now is node 2.
I'm sorry, Professor. In node 0, the 3 lines at the bottom, they don't mean anything, right?
Sorry, repeat the question again. In which, sorry?
In node 0, like there are 3 lines jutting out from the bottom.
Yeah,
Yeah, they
that
don't
doesn't mean anything. That's just a picture for ground. Sorry.
Okay.
This is just a picture for ground. So, oh, yeah, I'm sorry. Yeah, there are separate Zoom links for Monday and Wednesday. I should have, I'm trying to think of if there's, yeah, I don't know. My bad. Anyhow, you can go back and watch this lecture. Okay. Maybe I'll try to consolidate them. Maybe Zoom's pretty awesome. I wish I bought the stock a year ago. Zoom's pretty great. I'm sure they'll let me consolidate the links. Anyhow, so these are the 3 nodes, 1, 2, and 3. So 0, 1, and 2. Okay, so now we've selected a reference node and we assign voltage labels to the non-reference node. So this is V1 here, and this is V2 here. Notice that if this is 0 and this is V1, it means that the voltage drop across R1 is equal to V1. So that's kind of that's probably a source of confusion for some of you. If the voltage here is 0 and the voltage here is V1, then the voltage drop across the resistor has to be V1. You can choose anything to be a reference node, but I don't know. It really doesn't matter. It's just that for whatever reason, it's conventional or customary to put the ground at the bottom of the circuit because then voltage drops like from here to here. Voltage drops from here to here. Okay. All right. So each node voltage is the rise from the reference node to the corresponding non-reference node. So in other words, V1 is a voltage from here to here, and V2 is a voltage from here to here. All right, so now we're going to apply KCL. So we're going to apply KCL at 2 spots, node 1, node 2. Okay. And so what we do now is we label our currents. So let me clear this again. So, and I will now say, so this current here is given to us. It's big I1, right? 1. And then we define little I1 as flowing down here. We define little I2 as flowing from left to right. And we define little I3 as flowing down here. So we have to make sure that every branch that's connected to one of our non-reference nodes has a current label and an arrow. And so now we are going to apply KCL at this node here. Okay, so KCL, so first of all, how many currents are involved in this node?
Four currents.
4 currents. That is correct. right? So does anyone want to tell me the, I've lost my cursor and there's a chat. Let's see if I can get it back. You know what, I got a new computer. I'm hoping this will fix it next week. Give me a second. I got my cursor back, but yeah, it is 4, and I will show you now. No, I don't want to end a meeting. Okay. So this is 1, 2, 3, 4. It's like a 4-way intersection. And the KCL notice that I1 is flowing in, and then the other 3 are all flowing out. I1 is flowing out, I2 is flowing out, and big I2 is flowing out. Does everybody understand this equation here? Yes, no? Okay.
For I3, we don't include that because it's composed of I2, of little I2 and big I2.
That's a node 2. So what you're saying is correct, but that's not involved in node 1. That's
Okay. This is
right?
for node 1. Okay.
Yeah. So I2, big I2 plus little I2 does equal to I3, just like you said. So that's the equation at node 2. And so now you have, so that's the hard work. The hard work is writing down the KCL equation correctly.
Actually, I have a question.
Yeah, go ahead.
Shouldn't the big I2 be equal to the big I1 because it didn't go through any resistors, right?
Big I2 is just a current along this path. So big I2 is the current in this node here, right? So that's just one part of the 4-way intersection. So I2, little I2 and big I2 are 2 different currents. They have the voltage, they're parallel, but parallel means same voltage, not same current. So big I2 is a different branch than little I2, and so they will be yeah. I'm confident that you will get the hang of this once you've seen a couple of examples. So little I2 is the resistance is the current through R2, and big I2 is just, it's really the current that's coming out of this branch and coming back into this branch. Okay, so now the hard work is getting the KCL equation, and you guys jump in. If there's any more questions, please do just jump in. You have the 2 KCL equations, and now you're ready to substitute Ohm's law expressions for the little i's. Notice that I1 is equal to V1 minus 0 divided by R1. So let's move on here. So I1 here is by Ohm's law, it's V1 minus 0 divided by R1. Another way of stating this is that I1 is equal to G1 times V1. So G1 is the opposite, is the reciprocal of R1. Now, what about little I2? That's this current. The voltage across R2 is V1 minus V2, and the resistance is R2, which makes I2 equal to V1 minus V2 over R2. Right? So the current that flows from this point to this point is given by V1 minus V2 divided by R2. And what about I3? Okay, what are the, I3 travels from here to here. So it's V2 minus 0 divided by R3. So I want to stop at this point because this is like critical stuff for the rest of the course. And now you know that you know how to look at a branch and write its Ohm's law equation. So I just want to, if there's any confusion as to how we derived these three equations, please let me know now. Let me see.
So just to recap, G would be 1 over the resistance in this case, right?
Yeah, G1 is 1 over R1, G2 is 1 over R2, and G3 is 1 over R3. Yeah, so I'm not sure if the first half of the lecture will help you. I hope it does, but I'm not too confident that I did a good job in giving you the context. But I'll just repeat I2. So I2, maybe I really would just annotate. You know what? I'll kill the slideshow and I'll annotate it. So I2 goes from here. I2 goes from here to here, right? So the voltage here is V1, the voltage here is V2. So the difference in voltages is V1 minus V2, right? And that's this. And then R2.
Would it matter if we did V2 minus V1?
Yeah, that's a good question. So you would do V2 minus V1 if the current arrow is going this way, right? So you always follow the voltage drops from here to here. So you do V1 minus V2. But if the current arrow, if this current arrow is actually going the other way, you would do V2 minus V1.
But didn't you say before the node voltage is a rise? So wouldn't it be from the other way?
So let me see if I can draw a resistor. And then this will be plus, minus, right? And so if you have your, this is just a line, this is a wire, this is a wire, this is a resistor. And let's say that this is V1, this is V2. So if the current is going this way, you define it. You define that direction of the current arrow, right? And then this is R, this is the resistance R. You would say that V1 minus V2, because you said it's a voltage drop from V1 to V2 over.
Oh, that would be positive then, because V2 would be smaller?
Yeah, that's right, exactly.
Okay.
Right, that's right. Let me see if there's any chats that I haven't. Yeah, that's right. It's the beginning. It's the beginning of the arrow direction minus n, because we say that the voltage drops from here to here by a value of I2 times R2. So for I1, it will be V1 minus 0, because the voltage here is defined to be 0, divided by R1. So again, the voltage drops from here to here by a value of I1 times R1.
Makes sense, thank you.
So are we given I2? Is that why we don't have to solve for it?
we will be solving for it. So basically the picture that you're given is like this. So the question will say something like solve for V1 and V2, but in the process of solving for V1 and V2, oh, sorry, are you asking about big I2?
Yes.
Oh yeah, they'll be given to you. Yeah, it's kind of, they're always given to you. Yeah, that's a good question. So what we're doing here is what you'll see in just a second is you're gonna arrive at these systems of equations. So now you can combine, you have, it looks like you have 3 equations, but actually you only have, the 2 unknowns here are V1 and V2. So you can perform substitution. So hold on. Our KCL equations, if I just, let me give you the evolution, right? So these are our 2 original equations where big I1 and big I2 will be given to you. So you would know what the value of the current sources are. And then you apply KCL at the 2 nodes, which is what we did here. And then you substitute them into those initial equations to get this, right? So I1 is equal to I2 plus little I2, which is here, plus little I1, which is here, right? So this equation here is KCL of this node, where instead of, so the little I2 and little I1 are intermediate variables. They get replaced with voltages. And so what you end up with is 2 equations and 2 unknowns. And by the way, you can also write this in terms of conductances. So you can replace 1 over R1 with G1, and you can replace 1 over R2 with G2. And so, so the third step is to actually solve this equation for V1 and V2. Remember, you would know what big I1 is, big I2, big G1, and big G2. You would know the values for that. So again, you can use whatever technique you like to solve the system of equations. I like solving them in MATLAB, but again, you can use whatever method you want. So in matrix form, right, if you write this equation in matrix form, so let me see if I have room to write a matrix here. So in matrix form, this would be, let's see if I can. You know what, let me actually get rid of this. Let me freehand draw this. So in matrix form, you would have G1, G2. Oh, actually, never mind. I erred. So before that, let's actually, this is going to be our matrix. And what we're solving for here so first put in what you're solving for, which is V1 and V2. That's a 2. Trust me. And then so what is going to be the coefficient on V1, first of all? Well, the coefficient on V1 is going to be G1, right? Because that's plus G2 here, right? So we have G1 multiplying V1 and G2. So the coefficient here will be G1 plus G2. And what's the coefficient multiplying V2 in the first equation? Well, it's minus G2. So minus G2. Okay, so the first equation, and then what about this? The right side of the equation will be I1 minus I2. Okay, that's a 2. My 2 don't, forgive me. The second equation, let's see. Let's move this term here to the other side. And so what we're multiplying V1 is minus G2. And what's multiplying V2 is G2 plus G3. Okay, and then I2 is left on the right-hand side. So now what we've done is we've transposed this system of equations into a matrix vector form, okay, which is, now I'm gonna, what's the remote control feature? Oh, cool. That's awesome. Yeah, so this is our system of equations. That's what I was trying to derive for you on the previous slide. And so remember, the G's and the big I's will be given to you in the question. And all you would have to do is solve the system of equations for V1 and V2. All right. Let's do an example because that's ultimately the way that you're going to learn this. So we are given this circuit and we are asked to calculate the node voltages. So first of all, how many nodes are there? There's actually only 2 non-reference nodes. This is node 1. This is node 2. And this here is all the reference node. That's the ground. Okay, so we've already done the step of labeling the ground, which is over here, and we've labeled our non-reference nodes. So now we need to apply KCL. Okay, so remember that you're gonna have to label every branch's current. So let's call this I1, which is gonna be equal to 5. The current from here to here, we're gonna call I2. The current flowing down, we're gonna call I3. The current flowing down over here, we're gonna call I5. The current here is gonna be, which is gonna be equal to 10. And the current up here has to equal to 5. So you do have some flexibility here. The direction of I1 should not change, right? Because you have a current source here. And so it wouldn't make any sense to draw this arrow the other way. Similarly, the direction of I4 should be consistent with the direction of the current source with which it's in series. However, the direction arrows of I2, I3, and I5 can be whichever way you want. It's arbitrary, right? So if you and your friend drew your I2 in a different direction, then assuming you both did the work correctly, your answers would have the opposite sign. That's all that means. Okay. So we've selected our reference node down here. V1 and V2 are defined. This is node 1, this is node 2, and we have all the branches labeled with currents. So let's, well, let me give you the first node and then I'll ask for help for the second node. So notice that node 1 is a three-way intersection. Right, so we have I1 flowing in, you have I2 flowing out, and I3 flowing out. So I1 is on the left side, I2 plus I3 is on the right side. So we know that the value of I1 is equal to 5 amps. That's given to us. So plug in 5 for I1. And now let's apply Ohm's law for to calculate I2 and I3. Okay, so I2 is flowing across the from left to right across the 4 ohm resistor. So we have V1 minus V2 divided by 4. Right? That's over here. Right? Because the current is going from left from V1 over to V2. So the current, there's a drop of V1 minus V2 that's equal to I2 times 4. I3, on the other hand, is given by V1 minus 0 divided by 2. Okay, so first, is there any, if anyone has questions as to how this was derived, please jump in now. Okay, so who can help me? Who can help me with the KCL equation for node 2 over here? Who wants to take a shot at it?
Is it I2 plus I4 will be equal to I5 plus I1?
Excellent. Right. Oh, so before I did that, I guess you're gonna you could simplify these. This is just a simplification of the previous term, but what you were saying is absolutely correct. I2 plus I4 is equal to I1 plus I5. And then when your Ohm's law substitutions would be, so I2 is equal to V1 minus V2 over 4. I4 is given by 10. I1 is given by 5. And I5 is this current, is V2 minus 0 divided by 6. Right? And again, you do the algebra, and you can do them however you want. At the end of the day, you have 2 equations and 2 unknowns, and you can add the 2 equations. This is a case where you can easily do elimination. So you can eliminate V1 by adding these 2 equations. And you get that V2 is equal to 20 volts, and V1 is equal to 40 over 3. Okay, excuse me. Again, I'll pause just to give you guys the opportunity. I haven't checked the chat in a second. Okay, there's nothing there. If there's any questions as to what's going on, please go ahead.
Would the signs matter? Because I was also thinking of I2 plus I4 equals I1 plus I5, but then they're in opposite directions of each other. So would it matter?
Which 2 are in, oh, you're saying that I2 and I4 are in opposite directions?
Yeah, and I1 and I5.
That's okay. That's perfectly fine. Basically, what that equation is saying is that you can't, it's
No,
just
I get what it means. It's just like, does the signs matter in terms of the calculations and whatnot?
No, the only thing, as long as you write currents in equals currents out, you're following KCL. Okay, so we could use Kramer's rule, but I'm going to skip it because I think it's not a good use of our time. Okay, so now we arrive at some examples. So these are all good ways of practicing nodal analysis. So we're going to start off with the easy one. And I'm going to ask, so here, notice that the nodes have already been labeled. Right, so this is node 1, this is node 2, and this is the ground. And let's label the nodes I1. You know, it's pretty common to label nodes as going down, and then left to right is kind of depending on the circuit, but again, it doesn't matter which way you label them, but this is a common convention. So now, given this picture, who can help me write the KCL equation at node number 1?
So we're going to have the big I, 1 ampere. We're
Yeah,
gonna call
one.
I'm gonna call it no. Okay, 1. That's going in. So 1 equals I1 plus I2.
Excellent. And do you want to take a shot at defining I1 and I2 in terms of voltages?
Yeah, of course. I1 is going to be V1 minus 0 over 2 ohms, and I2 is going to be V1 minus V2 over, I can't see what that says.
6. Yeah. 6. Yeah, sorry. That's excellent, man. That's really great. So that's exactly right. I1 is equal to V1 over 2. I2 is V1 minus V2 over 6. That's exactly right. And then we can simplify this to get 4V1 minus V2 over 6. So this resistor here is 6 ohms, because I know the Zoom is blocking it. They need to get their engineers on that immediately. Who can help me with the KCL at node number 2? Someone in the back of the class. I can't do that game anymore where I say it has to come from the left side of the class or.
Okay, I'll take a shot at it.
Sure, go ahead.
You know, with my half class knowledge.
Yeah. Oh, that's awesome. Go ahead, man. It will be all the more impressive if you get it right.
So we're going from node 2, correct?
Yeah.
Okay, so is it plus 4A? Would it be, or would it be negative minus 4A?
It depends. Yeah, I mean, you can do either one depending on what you do with the other terms.
Okay, so minus 4A is equal to.
So let me help you out. So look at this node, right? Which currents are flowing into this node? Where my cursor is.
I2.
Yeah, so I2 is flowing in, right? So yep. I2 is equal to what?
I2. What do you mean? Like the it's 6.
Yeah. So no. So node 2, right? So sorry, the Zoom thing keeps coming down on me. It's driving me crazy. Hold on. So where my cursor is now, which nodes are flowing out of that node? Well, sorry, which currents are flowing out of that node? My bad.
I3.
And?
4.
And 4, right? So I2 is going to be equal to I3 plus 4.
Okay.
Right? And then do you want to take a shot at replacing I2 and I3 with voltages?
Sure. I'm just reading the previous.
Yeah, go ahead. So
the previous one.
Go ahead. I'll check the chats while you do that.
No,
That's okay. That's okay. It's perfectly fine. So I2 is going to be equal to V1 minus V2 divided by 6.
Okay.
And then I3, which is the one going down, is just V2 minus 0 divided by 7. Right, because you're looking to see there's a voltage for this I2, the voltage drop is from here to here. And for I3, the voltage drop is from here to here. This is one of those things where like, remember I said sometimes like you'll read a sentence and you don't understand what it's saying. and then somehow if you just keep reading it over and over, especially on like different days, all of a sudden it starts making sense. I think that will happen with KCL and nodal analysis for you guys.
Yeah,
But
I just I need to go over it a couple of
Yeah.
times for it to kind of make
for
sense.
real, yeah. It's okay. It's gonna increase my view count on YouTube. It's good. Okay, so let's yeah, so we have all we have to do now is the algebra. So the common denominator of 42, I guess. There may have been a smaller one, I don't know. 7v1 minus 7v2 is equal to 6v2 plus 168. In other words, 7v1 minus 13v2 is equal to 168. So now we have our two equations, two unknowns. This is our matrix equation. You don't have to do it this way. You like, for example, you could isolate V2 here and then substitute it into here. However you want to do it. I did Kramer's rule. I don't know what possessed me to do Kramer's rule, but I did. I got my determinants and I got my values. V1 is equal to negative 2 volts and V2 is equal to negative 14 volts. Again, you could have easily done this one with substitution. You didn't have to do Kramer's rule. Okay, so that's I'm not gonna go on to the other examples because I don't want to. This is an important part of the lecture, and we're doing well for time so far. So I'm gonna pause for questions on anything that we've covered today. Please feel free to jump in. All right.
So
yeah.
sorry. In
Go
addition
ahead.
to the sorry, I didn't mean to interrupt you.
No, go ahead.
In addition to both the lecture, the slides, and the textbook, are there any other resources that you could recommend for just giving a better understanding of KCL, KVL?
You know, yeah, I mean, there's gotta be, you know, like I am, you know, I am definitely not the world's greatest lecturer teacher. I mean, the world's greatest circuits teacher. I'm sure that if you like, I'm sure that if you search KCL, KVL on Google, like you'll get, you know, in general though, in all seriousness, when I was a student, I did like to consult different, like for me, because we didn't really have, the internet wasn't as, you know, widespread yet, but
You're dating yourself, Professor.
yeah, that's okay. So from us, it was like different textbooks, right? So we would like, there was always more than one textbook on whatever topic we were studying. And that would help. For some reason, like everyone has a different way of explaining a concept. And so it helps to get a different, you know, to get multiple viewpoints. And so I'm sure there's great content on YouTube for this stuff. The lecture slides are great for focusing you on what you're going to be evaluated on, like for this, you know, for the exam, stuff like that. There is going to be a homework posted soon. So look for that maybe as early as this weekend, but more likely next week. But yeah, I mean, I would use these are fundamental concepts that are not, the field of circuits is very mature at this point, which means not, you know, there are some fields like biotechnology that are evolving rapidly right now. This is not the case for circuits. These concepts are very much fixed, static. We know how circuits behave. And so, you know, there's an accumulated amount, I'm sure, of online resources for you guys to consult. I like the textbook. If you guys have access to it, if not, let me know. I think the textbook that does a pretty good job. But yeah, because the material is fundamental, there's almost an infinite amount of places you can learn this stuff from. And there are like some zero cost e-textbooks on circuits. There's nothing really that fits this course well, but if you like mix and match, you can probably find something there.
Yeah, I think it just what Bisma said, just practicing some problems, and then eventually the concept will kind of work its way into my head.
Yeah, it will happen. I'm sure it will. Like I said, it's not just like a lot of it is just like passage of time. For some reason, like you want to expose yourself to a concept as early as possible to give your brain enough time to assimilate that knowledge, to connect it to other bits of knowledge that you already have. I mean, that's really all learning is. Like you're connecting a new fact to something that you already understand, to a related concept. So you want to start that process early on as possible. And yeah, and I think with the homeworks, you will get a chance to practice all of these concepts and more.
Thank you.
No problem. The ground symbol is just to denote voltage by itself doesn't mean anything. It's like your voltage is only has meaning when expressed in relation to another point, right? So if I say that I finished or I just went running and my altitude at the end of my run was 100 feet above sea level, well, that doesn't tell you anything because you don't know where I started. Maybe I started at 99 and then I've only climbed 1 foot, right? So the ground tells you the reference point for your circuit. And so when you measure a voltage with a voltmeter, you always have 2 leads, right? You always have to connect. And so one of the leads is put on the ground usually. And that's the way you probe. So if you want to measure a voltage at 0.1, you would connect one lead here, another lead there, for example. So you always need to have a reference. All right, I've gone past the time. I hope that you guys all have a good weekend.
Still ask some questions.
Oh, you have questions? Go ahead. Yeah, you go ahead and ask questions.
Thank you.
It goes without saying that if any of you guys wanna bounce, by all means do so. Go ahead.
All right. Can we go to the slide where there was a big I?
Yeah. Do you have a slide number by any chance?
I'm not sure, but
I think it's probably
almost here. Right
this
there.
one.
Right there. Yes.
Okay.
All right. So is I capitalized here because it's DC, or is it just because it's given?
Both, yeah. Those are both correct. It's capitalized because it's a constant that will be given to you and because it's DC. So those are both correct.
And then the other I's they turn into AC?
No, they're going to be, so if you have a circuit that only has DC sources, you're only going to have DC voltages and currents.
Okay.
So we don't get to AC. Everything in this course is DC until like lecture 6, I believe, 5 or 6.
So another question. So I2 was given here, and we had to solve. I use Ohm's law to solve I2 and I1.
Yeah.
But can we like do Ohm's law for I2 just to see, like, can we even do it, because there's no resistors there? So how would it even look like?
Big I2?
Yeah, big I2.
No, you can't. That's the thing. There's no way of knowing what the voltage is across the current source. Like there's no law that can tell you how to solve for I2, big I2 here.
All right.
Yeah, unfortunately. And the same thing, the converse is true. There's no law to tell you the current through a voltage source, unfortunately, because what the current source does in practice is that it senses the voltage and it kind of a current source will adjust its voltage to always provide the required amount of current. So it has to listen to the circuit. So there's no way for you to compute it, you know, a priori.
And you said for a voltage source, it's true. What was that what you were saying?
Yeah, so for a voltage source, there's no way of knowing what the current flowing through it is.
Mm-hmm. Okay. And one last question, which is kind of, I guess I could look it up, but I always find that I have questions, but then I don't have time to look it up. So you mentioned that in the nervous system, there's positive charges moving.
Yeah.
Would that also include the brain? And then how would like the TDCS, which like measures the brain, does that turn, like, how does it measure positive charges? Like, I don't know. Do you have
That's a
any?
good question. So it's EEG that's measuring. TDCS is actually injecting charge into the brain. So TDCS will actually send like external currents into the brain, and what it will do is it will change. It will kind of increase charges flowing throughout the brain, and we're still learning exactly what that does to the cells. In terms of EEG, so basically, if you put two voltage leads on the scalp, anytime that some ions are moving in the brain, and therefore that current kind of propagates out to the scalp. And so if you think about a nerve cell as like a pump of charge, so it's pumping charge in and out of the across the cell membrane. So if positive charge is being pumped out of the membrane, you will get, because it's like a chain reaction, and that leads one of your scalp electrodes to actually at that moment receive an extra ion of positive charge, and it will increase the voltage across those two leads. So whenever something is changing at the level of the cells, and usually there's many cells that are changing at the same time, that will manifest as a different voltage between 2 points on the scalp. And it's a big problem to go from voltages on the scalp into what actually happened in the brain, but we sense those changes by measuring scalp voltage. So the voltage on the skin will actually change as a result of those ions being pumped across the cell membrane of the neurons. All right. So I am going to bid everyone adieu, except for the TAs who I'm going to meet with. So Sam, if you're still there, stay on, and we're going to discuss the circuits distribution. And now I'm going to say goodbye to everyone. See you all students on Monday.
Wait, I don't think there's class on Monday, but like you can.
Oh, Wednesday. See you all on Wednesday. It's good news. Not that I don't love you guys all, but it's nice to have a day off.
Professor, yesterday I was waiting for the TA and it was like almost for 1 hour, but the TA wasn't there. The Zoom ID you provided us.
The office, I think the office hours are probably starting next week, but I know they posted their office hours now.
Yeah.
You can always email. We should all provide our emails if we already haven't, and you can email them to follow up.
I think like you can just go on Slack and like
Or on
just
Slack, yeah.
send us an email, and I think it will be available.